Hello everyone and to Dr. Muhammad Arif. We are from Group 3. Today we are going to present about Bernoulli Principle Experiment. These are our team members. We have Hafiz, Aisha, Afifa and Govindra. For the introduction, Bernoulli principle is a fundamental concept in fluid dynamics that describes the behavior of fluid in motion, especially focusing on the relationship between fluid velocity, pressure, and potential energy within a system. Named after the Swiss mathematician and physicist Daniel Bernoulli, the principle is an cornerstone in understanding fluid mechanics, with application range from the design of aircraft wings to the function of blood flow in the human body. In simple terms, Bernoulli principle states that within a streamlined flow, a flow without a turbulence, an increase in the speed of the fluid results in simulation, decrease in pressure or reduction in the fluid's potential energy. The relationship can be mathematically present as P plus 1 over 2 rho V square plus rho GH is equals to constant. According to the equation, for an incompressible and frictionless fluid flowing in a steady state, the sum of the pressure energy, kinetic energy per unit volume, and potential energy per unit volume remains constant along any given streamline. The implications of Bernoulli principle are observable in variation phenomena. For instance, it explains why an aircraft wing generates lift as air flow faster over the curved top surface of the wings. The pressure above the wing decreases, creating an pressure difference that lifts the aircraft. The principle also underlies the operation of Venturi tubes, which are used to measure fluid flow rates by observing changes in pressure. In this experiment, Bernoulli principle is explored through measurement of fluid pressure and velocity at different points in a tube by varying cross-section area. By observing how the pressure and velocity change as the fluid passes through constructions. The experiment aims to confirm Bernoulli hypothesis. As the fluid speed increases in the narrow section of the tube, the pressure decreases, and vice versa. The experiment provides insight into quantitative relationship between velocity and pressure in a controlled environment, allowing a deeper understanding of the factor influence fluid motion in engineering and natural systems. The primary objective of this experiment is to demonstrate and validate Bernoulli principle by analyzing the relationship between fluid velocity and pressure within a flow system. Specific goals include measuring pressure and velocity, record the pressure and velocity of the fluid at different points along the tube with varying diameters. The second one is confirming inverse relationship, demonstrate that as fluid velocity increase in narrower section of the tube, the static pressure decrease constant with Bernoulli principle. The third one, applying theoretical calculation, use Bernoulli equation to calculate expected value from pressure and velocity and compare this with above data to assess the accuracy of the theoretical model. The scope of the experiment is to investigate the fundamental relationship between fluid velocity and pressure in a closed system, use, using Bernoulli principle as the theoretical basis. The experiment involved observing fluid behavior in a tube with varying cross-sectional area, allowing a controlled study of pressure and velocity change in response to change in the tube's geometry. By analyzing the pressure and velocity of the fluid at different points, the experiment aims to confirm the validity of Bernoulli principle and exchange our understanding of fluid dynamics in idealized condition. The theory and working principle. The Bernoulli principle is a fundamental concept in fluid mechanics that describes how the speed, pressure, and potential energy of the fluid are related in a steady, incompressible, and frictionless flow. Formulated by Daniel Bernoulli in the 8th century, the principle of mathematician expressed as P plus 1 over 2 rho v square plus rho gh is equal to constant. This equation indicates that in an ideal field, one that is incompressible and has no velocity, the sum of the pressure energy, kinetic energy per unit volume, and potential energy per unit volume is converted along the streamline. Key components of Bernoulli principle is pressure energy. This represents the static pressure, which is the force per unit area exerted by the fluid on the surroundings. In a closed system, pressure decreases as the fluid speed increases due to the conversion of energy. Kinetic energy. This term represents the energy associated with the fluid's motion. When a fluid flows from a wider space of the tube in a narrower section, the velocity of the fluid increasing its kinetic energy. Potential energy. Potential energy depends on the height of the fluid relative to a reference point. For experiment at a constant height, horizontal flow, the terms is typically constant and all often be understood.
So, scope and organics for this temperatures that we use in this experiment. So, we have the water inlet, second we have the info panel, third we have the flip valve, that's the control to control the pressure in the manometer, and overflow to remove all bubble and air in the pipe system. 7 manometer for recording the pressure. Measuring probe that control the pressure total for each point 1, point 2, point 3, point 5, point 6. And outlet valve, the water flow out, and the battery that we use to loop the uh, length for each point from one point to the one point. So here the methodology for this experiment. First, we must to switch on the main switch and the pump. After that, we must to open the control outlet valve slowly until maximum level to remove air in the pipe system. For the remove air from the pipe system, we must to open black cap and close back after all bubble removed from the system. So after we remove all bubble and air from the pipe system, we must to close back the control valve and the pump. After we must to slowly open white cap. That is a big valve until the manometer reach to 80 to 100 millimeter. Then close it back. After the system is ready, we must to switch on the pump again and slowly open the control and slowly open the apa ini? After that, we want to slowly open the inlet valve to see the until the manometer has reached its maximum and minimum reading. And after that, we want to reading that manometer pressure static for P1, P2, P3, P4, P5, P6, and the pressure dynamic, which adjust the pressure with the venturi meter. Uh, Adjust the pressure at the venturi. So after we get the uh, all the rating for P1, P2, P3, P4, P5, and P6, and the total pressure at the all point. We must to record the volume water collect at the tank with the time for actual flow rate Q. So here we collect 1 liter water, and after that we must record the time and how much time we must take for 1 liter water to collect. So after that, repeat step 7 and add for different flow rate means for the different flow rate Q, different flow rate of outlet outlet valve. So after the this experiment we must repeat 5 times. We must to repeat from step 7 and 8 from different flow rate uh, about 5 times. And after we have finished the repeat the step, we must to fully close the outlet valve and switch off the pump, switch off main switch at the back. Okay, thank you.
Next, this is our result for this experiment. We got 5 different reading for P1 until P5. Next, we move to our discussion for table 1, theoretical velocity at different points. So question 1, calculate the fluid flow velocities in the ventral nozzle at different points. Theoretical values, we got 0.0918 meter cube per second. And then by using the area and standardized reference velocity given, the theoretical values of flow velocity at each point can be calculated using the following equation. And then the second one is experimental velocity at different points. So this is the table about average hydrostatic. And then we use the formula to calculate the velocity. Next, for discussion, question 2, calculate the flow coefficient at different flow rates. So by the formula given, we calculate the flow coefficient where gravity is 9.81 meter per second, and the table shown that Qx meter cube per second, delta H, which is H maximum minus H minimum in meter, and we get flow coefficient for this experiment.
This is the graph for the experiment that we have done. We collected data at the 5 point along the ventral nozzle and used the average value to plot this graph, showing the variation in static, dynamic, and total pressure along its length. The graph shows the distribution of static, dynamic, and total pressure along the ventral nozzle. Static pressure, which is the blue line, decreased in the narrow section due to the higher fluid velocity, then increased as the nozzle widened. Dynamic pressure, which is the yellow line, increased in the narrow section as velocity increased, then decreased as velocity dropped in the wider sections. And for the total pressure, which is the red line, remained nearly constant, estimating energy conservation as per Bernoulli's principle. This pattern, this pattern illustrates how fluid energy shifts between pressure and velocity as it flows through changing nozzle section, confirming Bernoulli's principle. For the static head, the highest at wider section of the nozzle P1 and P4, and decrease the fluid move toward the throne where the pressure is the lowest. And for the total head, the sum of the static head and dynamic head. The total head remain constant along the nozzle if we neglect friction and other losses, according to Bernoulli's equation, because of the principle of conservation of energy. And lastly, dynamic head is represent the pressure due to the fluid kinetic energy. When velocity is increased, kinetic energy is increased.
So hello, this is a precaution that we must to alert during during to the experiment. So first of all, we must always alert Mr. Caution and handle carefully to avoid the battery breaking. After that, eyes must be perpendicular to the scale to avoid the parallax error. Next is make sure the manometer will fully connect to the pipe flow to ensure the flowing water to be smooth. And lastly, you must do not touch the switch with your wet hands and make sure you use with dry hand to avoid allergic shock. So, for this experiment, we confirm the Bernoulli principle by demonstrating the inverse relationship between fluid velocity and pressure. As the fluid velocity increases in narrow section of the tube, the pressure decreases consistent with Bernoulli prediction. This validates the principal accuracy in describing fluid flow behavior and illustrates in practical application in areas like venturimeter and aircraft wing design. Minor deviation from the theoretical value likely result from frictional loss and measurement. Limitation highlight real-world conflicts in fluid dynamics. Overall, this experiment undercover Bernoulli principle, vital concept in both scientific and engineering application. That's all for us. Thank you.